Hi, smart people. In this new opportunity, we are going to resolve a problem about moment of inertia. So, the problem says a uniform loop of mass m and radius r hangs in a vertical plane supported by a knife edge at one point on the inside of the circumference. Calculate the natural frequencies of small oscillations. Okay, guys, in this problem we have this loop. Okay, um, we have this loop and it's hanging at this point A. All right, so the first thing we have to do here is we have to know the moment of inertia of the loop. Okay, so the moment of inertia about the point A is this: I about the point A is equal to m r squared plus m r squared, and this is equal to 2m r squared. Okay, where this first term is the moment of inertia about the center. In this case is 0 about the center, and this is the moment of inertia m r squared. Okay, here I use the Steiner's theorem or the parallel axis theorem. Okay, guys, Steiner theorem. And what does this theorem say? Okay, this theory says that if a body rotates about an axis that is parallel to the axis passing through the body center of mass, then the moment of inertia is going to be I equal to the principal moment of inertia, in this case about the center of mass, plus the mass of the object multiplying the distance squared from the center of the body to the point about the body is rotating about. So that's what I use here. In this case, if we make a comparison here, this mr, I'm gonna highlight it with yellow. This mr is the moment of inertia about the center of the loop, okay, about the point O, right? And this mr squared is this term m d squared, where d is the distance between the center of mass of the object and the point where the object is rotating about, in this case the point A. So I'm gonna write it real quick here, real quick. ICM is the moment of inertia about the center of mass. Okay, m is the mass of the object, and d is the distance between the center of mass and the point where the object is rotating about. Okay, in this case is the radio, in this case the radio of the of the loop. Okay, guys? Well, so now we have that the moment of inertia in this case is 2m r squared. Okay, guys? We are gonna use the Newton's second law for rotation. Okay, we are gonna use the Newton's second laws for rotation. And what does it say? Okay, it says that the torque is equal to the moment of inertia multiplying the angular acceleration. Because if we see something here, for example, if this object is rotating, in this case rotating about the point A, it's gonna have an angular acceleration, okay? It is rotating about the point 8. Okay, so this object is going to have an angular acceleration and it's going to have a angular velocity as well. Okay, well, we come back here. We have the following. This second Newton law for rotation by definition is torque is equal to moment of inertia multiplying the angular acceleration, and in this case is gonna be equal to moment of inertia multiplying theta 2 dot, because we have that the angular acceleration is equal to theta 2 dot, or is equal to the second derivative of theta with respect the time. Okay, well, by definition the torque is going to be equal to, by definition the torque is going to be equal to, in this case it's going to be 2 minus W multiplying B. Okay, what is W? W is the weight of the loop, okay? And it's gonna be the mass multiplying the gravity, okay? And it is pointing downwards, all right? This force is pointing downwards, okay? It's pointing downwards. And B, what is B? B is equal to R sine of theta. Okay, why? Why it is like that? If we come back to the figure in the problem, here we have a triangle. If we look here, we have a triangle here, okay? We have this triangle and we have this angle theta. This is the radius, sorry. This distance is the radius. And this side is R sine of theta. Is the opposite is the opposite side, the opposite side. Sorry, I'm gonna give me a second here. Okay, this side with blue is the opposite side for of this angle. So because if the opposite side is by definition, in this case, r sine of theta. Okay, I'm gonna write it in a different place to have more space. Star here, this is star. Opposite side is equal to r sine of theta. Okay, it's clear, it's more clear here. Well, r sine of theta. Okay, that looks better. Okay, so why that side is the one we use is because that one is the side that contributes to the torque. This side, the one with green color, the adjacent side, it won't contribute to the torque. It won't contribute because it's parallel to the weight. It's parallel. This side, this green side, is the adjacent side, is parallel to the weight, and because they are parallel, that side won't contribute to the torque, but the blue one, the opposite side, is gonna contribute to the torque. That's why in the definition we use r sine of theta. In this case, r sine of theta. All right, so that's why we use that definition in this case. And this is the lever. This is the lever. In this case is the lever. Well, then we have I theta 2 dot equal to torque, right? But torque is equal to minus W times B. But W, what is W? Is this. And what is B? Is this. So if we replace these two definitions into this part of the equation, we will have minus mgr sine of theta. All right? But, okay, and the equation finally takes this form. So the equation takes this form: I theta 2 dot equal to minus m g r sine of theta. But for small oscillations means that theta is gonna be small. So we get that for theta is small, we have sine of theta is approximately equal to theta. And because sine of theta is approximately equal to theta, then we get I theta 2 dots is equal to minus mgr theta. Okay, guys? So now we take this term, the I is multiplying on this side of the equation. It's multiplying on this side. We are gonna send it to the other side to divide. All right? And when we do that, we get theta 2 dots is equal to minus mg r theta dividing the moment of inertia. Okay? But if we remember, we do this. Now we do this step. This term that is this all term, that is with this negative sign, is subtracting on this side of the equation. We are going to send it to the other side of the equation, and it's gonna to add, okay? So we are going to send it to the other side of the equation, and the chain and the sign of the sign is gonna change. It's gonna be positive. So we have theta 2 dots plus mgr theta dividing I is equal to 0. Okay, what I did is I sent this term to the other side of the equation, and I changed the sign of it. Well, but I is equal to mr squared. We know that in advance, okay? We know that. Okay, I'm gonna write mr squared. If we replace this term into this equation, we get theta 2 dots plus mgr theta dividing 2mr squared equal to 0. And I simplify these terms. By simplification, we do this. This one cancels this. This square cancels this, and the equation gets this form, like theta 2 dots plus g dividing 2r theta equal to 0. This equation has this form, theta 2 dots plus omega squared theta is equal to 0. And if we compare this equation with this equation, we get that omega squared is equal to g dividing 2r. And if we take root square on both sides of the equation, we have this cancels this, and then omega is equal to root square of gravity dividing 2r, and this is the natural frequency of the oscillations. So hopefully these problems helps you to understand some physics related with natural frequency of small oscillations. If you like it, please give me a like, subscribe in my channel, and share with your friends. Hopefully this problem helps you to go and to do well in your school or university. See you in the next video. Bye.